I'm in the afternoon. I woke up at like 4 o'clock this morning. So. My son was throwing up.
Sorry.
So.
All right, let's get started. We have our midterm exam on Wednesday, and I do plan on talking about that a little bit at the end of class. So make sure, like, when I get to about 12:40, what time do we end? 12:40? 12:40. Yeah, so about 12:30. Don't let me go past 12:30. That way I can talk a little bit about the exam.
Hey, quick question. Do you have
Yes.
attendance?
Do I have attendance? I do, yeah. Why? Yeah. Do you want it right now?
That way you can
Okay. Like I would forget.
How many black lines do you have?
Let's see. Yeah. There. All right, so we are going to start 11:7. I don't think we'll finish it. Let's see how far we get. I do plan, this section, 11:7, has 2 parts to it. And I plan on, at a minimum, having the first part on the exam. The second part we probably won't have, all right? Because we're probably not going to finish it. So we are going to now talk about maximum and minimum values of functions of 2 variables. So we are first going to do a review from Cal 1. It's sections 4.1 and 4.3 out of the book. Now, these are 2 separate concepts. All right? And what we had back then was finding the max. Actually, I should say the absolute max. Max and min of continuous function on a closed interval. So we're doing a quick review of Cal 1. So when we were in Cal 1 and we had a function that was continuous that we could draw without picking up our pencil, basically, and it was defined on a closed interval, let's say AB. If it's a continuous function, you're guaranteed that the function will achieve a maximum, absolute maximum, and an absolute minimum value. Does anybody recall the method that we used to find the absolute maximum and minimum values of a function on a closed interval? Okay, set the derivative equal to 0. That is correct, kind of. Don't need that for closed interval, though. If it's an open interval, then that's what we're going to do. Okay, so we want to find where the derivative is 0. Also, where the derivative might be undefined. Okay, those are called critical points. So the procedure to do this is actually called the closed interval method. And if you're following along in the book, if you just want to go back and review this on your own, I'll tell you what page it's on. Let's see here. Page 207, about 3/4 of the way down the page, it's called the closed interval method right here. It says, to find the absolute maximum and minimum values of a continuous function on a closed interval AB, the first thing you do is you find the critical numbers of the function. So the critical numbers are where the derivative is 0 and where it's undefined. So first step, find critical numbers. Does this sound familiar to you? I know Cal 1 was so long ago. Find critical numbers. In other words, you figure out where the derivative is equal to 0 and where the derivative is undefined.
Isn't that also the turning point of the function sometimes?
turning point.
Like
for like a cube function.
That's second derivative. Are you thinking about concavity?
I think so, yeah.
Okay, so those are called inflection points. I don't know if that's what you're referring to. But here we're not, that's not part of this closed interval method. We find the critical numbers, and then really the next part is, they have it in two different parts. You're going to basically take the critical numbers and plug them into the function. And you're going to also plug in the what? Both of the endpoints. So that's the second step, is evaluate the function f at critical numbers and the endpoints. And what are the endpoints? A and B, right? So you just plug those numbers into your function. And the biggest one you get out is your maximum, and the smallest one you get out is your minimum. And that's it. So step 3 is just compare. All right, let's do an example of this, and then I'm going to move on to the next method after this. All right? So an example of this, let's say we had a function f of x equals 3x cubed minus 4x squared. And we want to look at it on the interval -1, 3. And I want to find the absolute maximum and absolute minimum. All right, so you first have to ask yourself, is this a continuous function?
Yes.
Why?
Polynomial.
It's a polynomial. So all polynomials are continuous. Good. And is it on a closed interval?
Yes.
Yes. Okay, so I can use this method. So the first thing I'm going to do is I'm going to find the critical numbers. So I take my derivative. What is the derivative of this function? 9x squared minus 8x. All right. And now, once I have the derivative, I just set it equal to 0, and then I also have to figure out if it's ever undefined. So if I take the derivative of this and set it equal to 0, then that means I'm taking 9x squared minus 8x equal to 0. And I made this real easy to work with. Just factor out a GCF here. X comes out. We get 9x minus 8 equals 0. And so you get two solutions. X is 0, and x is 8/9. Now, when you get these two answers, we want to plug them in to the original function. But you have to make sure that these two answers live inside this interval. Like if this had come out to be 4, let's say, then we would not check it because it's not inside this interval. Make sense? OK, so now let's plug in. So step 2, I get to plug those numbers into my function. So for step 2, I'm going to evaluate the original function, not the derivative, at 0, the original function at, oh no, not 0. Yeah, OK, we did have 0. I'm not doing this in any particular order. 3 and then 8/9. I didn't go in any order here, right? I just kind of listed them out. So what is f of 0? 0, that's the easy one. F of -1. -3 minus 4, -7. F of 3. 27 times 3 is 81. 3 squared 9 times 4, 36. 81 minus 36. Is it Monday or what?
45.
Okay. 45. All right. 8/9. Now, 8/9, this is going to be kind of tough. So let's just do it with the decimal. So get on your calculator, do 8 divided by 9, cube it, do all that, and see what we get. when someone gets an answer, you can let me know. I'm going to graph this while you're doing that.
Negative 1.05.
Negative 1.05. So we had 3x cubed minus 4x squared. Okay, let me make this bigger so you can see this. Here's the function. And you can see at -1, we're at -7, right? Do you all see that? And then at 0, we were at 0. Then at 8/9, we're at like -1 point something. And then at 3, we're way up here at 45, which I'm not going to go to. So it looks like the lowest point's the bottom left and the highest point's the top right. Okay? So it just turns out, what'd you get? -1 point what? 0.5. Okay? That our maximum, where would our maximum be?
45.
Okay, so we would have, this is where our maximum is, right?
Yes.
This is where our max is. And our minimum is this right here. Now, we have to be clear on something. The maximum value is 45. It occurs when x is 3. The minimum value is -7. It occurs when x is -1. Right? Okay. That was kind of a boring problem because it would have been more interesting if the maximum occurred somewhere inside the interval, but it turns out that the max and mins were just at the ends. It's not always that case. All right, that's just to remind you how we did that. Did that look familiar to you from Cal 1? Okay. Now, what we also need before we move into this section is to remember how we find the maximum and minimums of a function that is not on a closed interval. And the issue with that we run into is that it becomes very difficult to find what we call the absolute max and min. So here, when we don't have a closed interval, we have to talk about just local maximums and local minimums. So, all right. So this is the second topic here. Finding local max min of a function, and that's it. I'm not saying closed interval, I'm not saying open interval, I'm just saying we've got a function, how do we find its local high and low points? Now, there's several ways to do this. One way is to, and let's draw a picture here. What if I had this right here? We would have two local maxes, right? These would be local max.
Would that be the absolute max?
Well, we wouldn't know that. From the picture, it does look like it, okay? But because when I draw these arrows, it kind of implies that it's not going to go like this. But we can find these, and the most we can say that it's locally the highest point. It might turn out to be the highest on the entire function, but you would have to investigate the function a little further. Yeah. But they definitely qualify as being local maximums. And then this one right here is a local minimum right here. All right. Now, when we go and try and do this, what we did, anyone remember what we did? I think this is what you were referring to a second ago. Still have to find the critical numbers. Okay, so you find the critical numbers. Okay, that's where the derivative is 0, and that's where derivative is undefined. Now here's where there's two different methods. One method is, and this is the one I prefer, is to do a table, make a table. and test points into the derivative. Now, if you don't know what I'm talking about there, I'm going to do an example. All right? I like that method. What we're looking for here, okay, what we're looking for here is when our derivative tells us we go up and then down, we know we have a local maximum there. And if our derivative goes down and then up, we know we have a local minimum. All right, so I'll do an example, but that's my preferred way of doing it when I'm teaching Cal 1. Now, we also have what's called the second derivative test. So the second derivative test allows us to find local maximums and local minimums also. The only drawback to the second derivative test is that it does not identify things like this. So like if I have, let's say I had a function that does this. The second derivative test would find this. It would find this as being a local maximum, but it would not find this because I have a corner, a cusp or a corner. So when you have that, the second derivative test fails. How many of you are familiar with the second derivative test? Yes? Okay, so again, just to give you a reference, the second derivative test is on page 221. And what it says is that if you look at a function and the first derivative is 0, then you take the second derivative at that point. And if the second derivative is positive, then you have a local minimum. And if the second derivative is negative, you have a local maximum. So let me explain why it works that way. So imagine that I tell you this. Let's say that I have a function and that you know at this point A that on that function the first derivative is 0. Okay? That means that you know that the slope of the tangent line is flat there. That's not enough to tell you whether or not it's a local max or a local min. But if I then tell you that the second derivative, so I have that the first derivative at A is 0. That's what that means, right? But if I tell you the second derivative at A is negative, then that means it has to be concave down, and which means that you would have to have a local maximum. Understand? So this would correspond to a local L max. Is that right? Local max. If you have the first derivative 0 and then the second derivative is positive, then you have a local minimum. Do you see, though, how this would not find this one? Because the requirement for the second derivative test is that you have the first derivative be 0, and it would be undefined here. Using this method with the table, you can actually still get this guy, because you can see where the derivative will go up and then down. So this, to me, is a little... The second derivative test is, don't get me wrong, it's quick, it's fast, it's useful. But it's not as powerful as this method because this won't miss these types of things. All right, that's it. That's how we do it. Let's run through an example just to make sure we're all on the same page. I guess we'll be nice. This is just an example. This is just to get us familiar. Let's just take a nice little, how about the same one we just did? Was that it right there? Right? So the way that I would do this if I was trying, notice I don't have a closed interval anymore, right? The instructions here are to find local max and min, right? Find them, all of them. So we're going to take the derivative, right? Set it equal to 0. So I take my derivative, which was 9x squared minus 8x. Set it to 0. And what were our solutions? 0 and 8/9. By the way, I did not try and figure out if my derivative was undefined. I never looked at this, did I? Does anyone know why I skipped over this part? Because it's a polynomial, it's always defined. So I mean, I did think about it, but I forgot to put it up there that I hadn't considered it just because that was a polynomial. I'm looking for things like division by 0, roots of negative numbers, things like that. That's when I would need to be worried about my derivative being undefined. Okay, so now here's where I was saying you make a table. This is the way I do it. I draw the number line, and I mark out my critical numbers, 0 and 8/9, just make sure they're in the right order. This partitions my number line into 3 sections. And then what I do is I pick test points. And these test points have to be here, here, here. And what I'm doing is I'm just trying to see whether or not my function is going up or down here, whether or not my function is going up or down here, whether or not my function is going up or down here. So what I do is I pick these test points and I plug them into the derivative to see if I'm increasing or decreasing. So I'm going to plug like -1 in here, something between here and here like -1/2 or 0.5, and then over here 1 would work. Yeah, I'm not sure why I put that negative there. No idea. Thank you. All right, these get plugged into the derivative. This is the mistake I see students make. They plug it into the original function. That's not what you want. You want to know what the derivative is doing. If the derivative is positive, you're going up. Derivative is negative, you're going down. So I'm going to plug -1 into the derivative. So f prime of -1. What would that give us? So I'm plugging it into here. 17? Positive, right? So that means my function f is going up here. If I plug in 1/2, I'll get a negative, okay? So that means my function is going down, and if I plug in 1, I'm going to get a positive again, so I'm going up.
So in the last one, you get, like, you plug it into the original one, and in this one it's in the...
That's right. And on the first one, we also plug in the endpoints, okay? Because if you have a continuous function on a closed interval, you're guaranteed that the max and mins are going to happen at either the critical numbers or the endpoints. It can't happen anywhere else. So we just skip over this and just plug them in and compare them, because we're going to have a finite number of points to compare. So just compare them. Yeah. Okay, so what can I say? I have a local max, right, at x is 0, because I know that my function goes up and then down. So I have a local maximum there. Now, what would the actual value, what would the value be? What would that local maximum value be? The value would be f of 0. Plug in 0 into the original function, spits out 0. Then I have a local minimum at x is 8/9. And we plugged in earlier, didn't we? Yeah. The value was f of 8/9 was -1.05. So we are not saying that this is the highest point on the whole graph and this is the lowest point on the whole graph. We're not saying that. We're saying locally this one is like the king of the mountain, right? This one's like the valley, the bottom. But outside of that, we don't know. The function could be doing a lot of different things. All right, we good? Let's move on. So our goal now is to extend these two concepts to surfaces. In Calculus 1, what we do, the order we do this is the order I presented it to you. We do the closed interval method first, and then we do the more abstract open interval, just no closed, and you do the little table thing. That's the order we do it in Cal 1. In Cal 3, we're going to be looking at surfaces, all right, and trying to find highest and lowest points. So like if I have a surface here that's kind of cool to look at, so this is a cool little surface, like little ripples in a pond kind of, right? And we could try and find all these little local maximums and local minimums, right? Now, we could start out with like a closed interval method first and then go like the open interval like we just did. But in this, it's actually easier to do it on the open interval first than it is to do it on the closed interval. So the first section is to say, hey, let's say we have a function, a surface. Let's not restrict its domain at all, and let's find the absolute max and absolute min. We do that one first. Or sorry, local max and local min. I said that wrong. Then after that, we restrict the domain and find the absolute max, absolute min. That's harder. So this first part, where we don't restrict domain, is the part that'll be on the test on Wednesday. So here we go. That's the same picture, just different colors. And then I actually took it from the book. This is the picture in the book. I like this better. You like that better? That's much nicer. But this is the picture in the book. All right? So they call this an absolute maximum, a local maximum, absolute minimum, local minimum. All right? Just same concept, right? Now, we have definitions of those. I'm not going to read this out. Okay? I'm not going to read this. You can read this yourself. Just make sure that we understand that when you talk about a local maximum or a local minimum, there are two things to look at. The point at which it occurs, and then the value it's actually achieving. So when you say local minimum value, that's the z-coordinate. That's the height of the function, as opposed to the ordered pair AB, which is the actual input that created that output. You remember how I wrote down just a second ago, like the local max occurs at x equals 0. It has a value of 0. Like, we have to be able to distinguish between the two things. And then we have a very nice theorem. It says if f has a local maximum or minimum at a point AB and the first order partial derivatives of the function exist, then the partials will be equal to 0. So do you remember when we were finding critical numbers just a second ago? The first thing we did was we set the derivative equal to 0. This theorem is telling us that, look, if you have local maximums and minimums, if you've got these hills and valleys, right? If you have them, then your partial derivatives at those points will be 0. So we're going to do the same thing we did before. We're going to set partials equal to 0 instead of just the derivative. We have to set each partial equal to 0. And then for this, we're actually going to use the second derivative test, but not the one from Cal 1. This is the Cal 3 version of the second derivative test. And the calculation is a little bit involved. It looks worse than it is. What? I'm zooming in and it got smaller. That's interesting. That's really weird. Okay, I don't know what happened there. All right, so this is if we're going to like sum up what it is this first part of this section is about, it is this right here, the second derivative test. Suppose the second partial derivatives of a function are continuous on a disk with center AB. All that means is that we have a point that we're plugging into the function and that the function is defined near there. We don't have any crazy asymptotes happening. So it's defined. And suppose that the partial derivatives, both the partial with respect to x and the partial with respect to y, are 0 at that point. That is, that point is a critical point of the function. Then we will let d, we are going to define this quantity d, be the second partial with respect to x at AB. So remember the second derivative tells you concave up, concave down? This is like we're taking the concave, we're checking for concave up, concave down in one direction. And then we do that and we multiply it by the second partial with respect to y. So we're checking it in the other direction. We're trying to see, I mean, what if they're both concave down? Like what if this was concave down, we would have negative, right? And then here we would have negative. So when we multiply the two together, we should get positive, right? But then from that, we need to subtract, we need to look partial with respect to x and y. So what order do I do that in? X first, then y. We're going to look at that, and we're going to square it, which means we're going to multiply it times itself. So it's like we're looking almost like in 3 different directions, and we're trying to figure out if we're concave up, concave down. Once we compute this quantity, we have to look at it, and we have to say, did we get a positive number or a negative number? If you get a positive number, there's 2 different things that could be happening. If this is positive, and this second partial with respect to x, that means this piece right here, if that piece was also positive, then we're at a local minimum. If this calculation of d is positive, but this part is negative, then we're at a local max. And if the d is negative, automatically we are not at a local, it's not a local max or a local min. We call these saddle points. You've seen a saddle before, right? It's like curved like this in one direction, but like this in the other direction. So I don't know if you remember in Cal 1 we had this happen with like the x cubed function. This point right here was a critical number, right? The derivative is 0 here. It's not a local max, it's not a local min. It's neither. The equivalent to that on a surface is like a saddle. And so this last case is the case where you have a saddle happening. With me? Yes?
You said the order matters, the partial of x and then y?
This one right here.
In Clauset's theorem, doesn't the order not matter because of the equal to each other?
Well, as long as we have the conditions met for Clauset's theorem, because remember Clauset's theorem, we had some conditions for it. Not in general, those partials are not the same. All right, here we go. Time for an example. We're calculating d. That's all we're doing. Calculating d, figuring out which of these three scenarios it is happening.
So we don't have anything to do with f of y.
Well, just in this computation right here, but other than that, in the checking to see local max and min, we do not have to look at the second partial with respect to y. Only the second partial with respect to x.
Which page is this on the textbook?
Good question. This is 11. What is it?
671.
671. Thank you. All right, so find the extreme values, which means find the local max and local mins of this surface right here. I don't think we're going to have any. What do you think? Looks like a saddle, doesn't it? So I should get a d equals, d is a negative number here. But let's go through the process. First thing I'm going to do is find my critical numbers. So I need to find the critical numbers. And to do that, what do? Partial with respect to x equal to 0, partial with respect to y equal to 0. That's what I need to do, right? Figure out where that happens. Understand, these have to both be true. You're going to find a point, AB. All right, we're trying to find a point AB right now that makes this true and this true at the same time. That's what we're looking for. Not you need both of these to hold at some point, not just one of them. So let's take what is our partial derivative with respect to x?
Negative 2x.
This is negative 2x equals 0, right? That's me setting the partial with respect to x equal to 0. How about partial with respect to y equal to 0?
2y.
2y equals 0. And the solution to this is just x is 0, right? And the solution to this? Y is 0. So in order to make my partials equal 0, those two partials equal 0, I'm going to have to choose x to be 0 and y to be 0. So the AB that I was looking for should be the point 0, 0. Now this is a very simple algebraic problem, right? There's no craziness. We're going to get crazy. We're going to have some algebra to do, some equations to solve, but this is just so that we understand the concept. So now what I'm going to do is I'm going to calculate d at 0, 0. All right, what do we need for d? We need second partials, don't we?
Yes.
Okay, so let me get my second partials. Partial with respect to x and then x again is what?
Negative 2.
Negative 2. Partial with respect to y, then y again
It's 2.
is 2. What's the partial with respect to x, then y? I need those three pieces in my calculation for d, don't I?
Negative 2.
So what's the partial with respect to x? Let me put them up here. I never put them here. Partial with respect to x was negative 2x. Partial with respect to y was 2y. Then I set them equal to 0, right?
That's the second.
Pardon me? What is the partial with respect to, this is the partial with respect to x. What's the derivative of that with respect to y now?
0.
0. So this is 0. Make sense? Now what I'm supposed to do is I'm supposed to take a look at those. The calculation for d is the partial with respect to x twice at 0, 0. Then the times the partial with respect to y twice at 0, 0. And then minus the partial with respect to x then y at 0, 0. And then that quantity squared. So normally I would be replacing the x and the y in these three equations with 0, 0. But do you see that our partials don't even involve x and y? They're just constant. So in this problem, there's nothing to plug in. All right? So f(x(x) is -2 times 2 minus 0. This is -4. That's less than 0. D is a negative number, which means 0, 0 is a saddle point, right? There's no local max or min there. Does this make sense? Okay. So my conclusion is that 0, 0 is a saddle point. And you can see it from the picture, right? That it looked like a saddle.
Will we have pictures on the exam or no?
No, there's no pictures. All right, so find the local maximum, minimum values and the saddle points for this one. So sometimes, if it's not that hard to do, you can just get all your partials that you need for the problem from the beginning. You're going to need partial with respect to x, then with respect to x again, and then you're going to need it with respect to y, and then y again, then you're going to need it with respect to x followed by y. So if you want, just get all of them to start, and then you can start your work. Partial with respect to x, 4x cubed minus 4y. Partial with respect to x, then x again. 12x squared, okay. Partial with respect to y. 4y cubed minus 4x. And then partial with respect to y followed by y again, 12y squared. And we need one more for the formula, partial with respect to x followed by y. So that's this one with respect to y. -4. Now these right here, this one, and this one, those are used for the calculation of D, right? The other two are where we're going to get our critical numbers from. All right, critical number time. Let me set the partial with respect to x equal to 0. So I'm going to get 4x cubed minus 4y equal to 0. I also need to set the partial with respect to y equal to 0, which means I need to set 4y cubed minus 4x equal to 0. So can you already see that the algebra of this one's a little more complicated than the one before, right? These aren't just simple little linear equations. Any ideas on what to do here?
X with respect to y and then put it in the other equation.
You're saying solve, did you say solve this one for x? You could solve this equation for x, and then you could take that and plug it in here, right? And then you'd have an equation with just y's in it. That is good. We could do that. I'm not saying it's right or, I mean, that will work. Any other suggestions? You can set them equal to each other because they're both equal to 0, right? If these are both equal to 0, then they have to be equal to each other. So we could set them equal to each other, and then maybe we could get it that way. All right? But at this point, it's purely up to you to try and figure out the x and y's that make this true. Is it obvious to you that the point 0, 0 appears to work? If x is 0 and y is 0? Would it satisfy both of those at the same time? Yeah, but that's not the only one, and you need to find all of them. So what do y'all want to do? Do y'all want to solve this one for x and then plug that into that one, or do y'all want to set them equal to each other?
I'd solve it for x.
You want to try and solve this for x? Okay, let's try that. So if I'm going to take this and solve it for x, I get 4y cubed equals 4x. Divide both sides by 4, and I get y cubed as x. I can take that, and I can go into the other equation now and replace x with y cubed. So this equation now becomes 4y cubed cubed minus 4y equals 0. And that's 4y to the 9th minus 4y equals 0. And that looks like I can solve that. Just a quick factoring right now. Everyone, y'all clear with the fact that this is going into this? That's what happened there. I substituted that back in there. Factor out of 4y.
Y to the 8 minus 1.
So 4y comes out, y to the 8th minus 1 equals 0. And now that we've factored it, you set both factors to 0.
Y is going to be 0.
So I'm going to do 4y equals 0 is one equation. The other one is y cubed minus 1 equals 0. This is just y is 0. This one, y cubed is 1. Right, plus or minus. You take the 8th root on both sides, and when you do an even root, you have to do plus or minus. So we're going to have positive or negative 1. So it looks like, here's what I've got for my y's. I can have 0, I can have 1, and I can have negative 1, right? But now I need to figure out what the x's are that correspond to that. So I'm going to take these y's, I'm going to take them, and I'm going to go back to this equation for x and figure out what x would be for each of these y's. In other words, I have to look at this as being 3 different points. I have 0 here for the y, I have 1 here for the y, and I have negative 1 for the y. Those are my 3 candidates for y. Now, if y is 0, what's x? 0. If y is 1, what's x? And if y is negative 1, what's x? Negative 1. I have 3 critical points. I have to calculate d for each of these. Questions? All right. D time. So the notation the book uses, since we have more than 1 point, they do this. They say, what's d at 0, 0? Well, that's the second partial with respect to x at 0, 0, times the second partial with respect to y at 0, 0, minus the partial with respect to x, then y at 0, 0, oops, and then that quantity squared, right?
0.
What? At 0, 0. Oh, did he say that's 0? Is that what you said?
Yeah.
What part's 0? What is this one right here? fxx 0. Well, here it is, right? I plug in 0 for x, so it's just 0. What's the partial with respect to y at 0, 0? 0 again. And then minus, now let's check this.
16.
This one is always this, right? Okay, so negative 4 squared, but it's being subtracted. So this is negative 16, which means that I have what there? Saddle. Okay? So we have a saddle point at 0, 0. Now, I like this notation here that I have a saddle at 0, 0. But here's the way I would prefer you to do this. And you'll see why on the next step. Instead of saying I have a saddle at 0, 0, I'm going to say I have a saddle at 0, 0, 1. Why do you think I like this more than this? Yeah, it gives you the z coordinate too. So not only do you know where it happens in terms of its domain, like the point that's being plugged in, you know what the z value is, like how high it is. It's 1 unit high. So it gives you all the information as opposed to just where it occurs. Oh, where did I get the 1? Yes, I'm sorry. Where did I get the 1? I'm plugging 0, 0 into the original function. And when I plug 0, 0 into here, I get 1. It's the output of the function at that point. Now, it's a saddle point, so it's not very interesting. But, all right, now let's do D11. We never talked about what happens if you calculate D and get 0. We only talked about D if you get positive or negative, right? What if D is 0? What do you think? It's the test fails. The second derivative test doesn't work. In other words, it might be a max, might be a min, might be a saddle, but the test is not providing you enough information. So you'd have to use some other method. It's not going to happen to you. I'm just telling you, like, if you get D is 0, you really don't know anything. All right, what's fxx1? Let's see, fxx 1, 1, fyy 1, 1, minus fxy 1, 1 squared. So if I plug in 1 for x and 1 for y into this, I get 12. If I plug in 1 for x and 1 for y into this, well, it only has y, so it's going to be 12 again. Minus, this was always negative 4, and squared. So we're going to get 144 minus 16, and I can tell you right now that's a positive number, right? So D is positive. When D is positive, what do we need to do? Check this partial with respect to x twice. That one right there. And it was what? 12, and that's positive. What does that tell you? Local min. So the way I remember this is that this is a second derivative. Second derivative is like concavity. And positive concavity means you're like this. So you would be at a minimum. Okay? So I have local minimum. That's my conclusion. Understand? So I have local min at 1, 1, negative 1. Right? Because you're plugging in 1 for x and 1 for y. 1 for x, 1 for y. And you should get 1 plus 1 minus 4 plus 1. So this should be negative 1. This is pretty straightforward. I think, as you're going to see, the hardest part of this is going to be finding the numbers. The actual points, the critical numbers, or the critical points, that's usually the hardest part of these problems. The algebra. Because so far, the algebra has been pretty clean. All right, how about D negative 1, negative 1? Think about the computation. Is anything going to change? No, because when you plug in, this was x squared, this was y squared. So aren't you going to have the exact same result that you just had? You will. So I'm not going to go through. I'm just going to say that it's positive. And also that the fxx part was positive. And therefore, our conclusion is that we have a local minimum again, right? At negative 1, negative 1. Does this change? No. We're still going to get negative 1 out. You can plug it in, but that's it.
So this one doesn't have any local maximum?
Has no local maximums. Whoa. Whoa. Saddle, Max. Wait, I have it upside down. There. Now, this thing is cut off because the computer has to stop it. This thing keeps going up, almost like parabolically. It's like a 4th degree polynomial. It's growing real fast. All right, let's take a look at another one. Does it seem kind of nice? I don't know. To me, it seems nice that we can find the local maximums and minimums of a surface with relative ease. I mean, it's not a whole lot of work that required, right? I mean, it's pretty nice that we can do that. All right. Why don't you first just list out all the partials? Partial with respect to x, x, y, y, x, right? Get all those, and then start messing with the algebra on that. You want me to give you a little time? I can give you a little time, see how you do with it. I don't remember how the algebra is for this one. It'll be interesting to see what you do. No. So I've put the partials up there just so you can check. Well, the algebra on this one's not bad. Who's already got the algebra for this going? What did you do?
I solved for x.
Just solve for x over here?
Yeah.
Okay, and you got x was what?
The cube root of 8.
X cubed was 8, so x is the cube root of 8, which is just 2. So
And then you put it back into.
Yeah, plugged it in
just
there.
plug it back in?
And
Yeah.
I solved for y, and you get y is.
I was asking if it's only 2 or plus or minus.
Nope, it's only 2 because it's a cube root. For odd roots, it's only one sign. So this is actually not bad because we know what x has to be. That's the only, x has to be 2 for this to be true. So now what we're going to do is we're going to take that 2 and plug it in over there and solve for y. So plugging in 2 for x, you get 12y plus 48 equals 0. So replacing the x's with 2's, so y is, what is that, negative 4? So we only have one critical point. Our only critical point is the point 2, negative 4. That's it. CP, critical point. This is it. I was hoping the algebra was going to be a little harder than that one. Trust me, it's coming. It's coming. All right. I need to calculate d there. So d at 2, negative 4. Let me try and do this without writing the whole formula. I need to plug in 2 and negative 4 into fxx. So when you plug in 2 and negative 4 here, what do you get? Negative, is that negative 48?
No, you get 72.
And then,
And then,
no? 6 times 2
no, that's right.
is 12 times negative 4, negative 48, plus 24, negative 24, right? So this is negative 24, and then times 0. Oh, it doesn't matter. Minus, and then fxy is just going to be 12 squared, which this is going to turn out to be a negative number, right? Which means it's a saddle. Boring. So we have a saddle point. Has anyone figured out what the z coordinate is?
48.
It's 48 at 2, negative 4, 48. There's our saddle. Because the computation of d was negative. This is 0 minus 144. All right, we've got to get some tougher algebra going on here. This is still very, very basic. Ah, okay, that looks better. Oh wait, we didn't look at the picture. We don't need to look at the picture for that one. Let's do this one. I think I'm going to take my time on this one. I'm not going to do all the derivatives first. I'm just going to do the partial with respect to x and y first. Partial with respect to x, all right, is itself, e to the anything, the derivative of e to the anything is itself, times the derivative of what was up in the exponent with respect to x, which is only just negative 2x. All right, now the partial with respect to y is the same thing, e to the 4y minus x squared minus y squared, but then times the derivative of what's up there with respect to y, 4 minus 2y. Ooh, okay. If you take this